Okay, so we're going to move on to what a whole of a rational function is. And to describe a whole, let's take a look at the first statement here. It says sometimes the numerator and denominator will share a common factor. When this occurs, there exists a point of discontinuity called a whole. So a whole is a point on the graph where it's not defined. So there's actually a break at that point. So to show you this in detail here, consider this rational function here. Y is equal to x squared minus 4 over x plus 2. So what I want to do is just find the NPV, so the non-permissible values of this rational function. To find the non-permissible values, you're always looking at the denominator. You're going to set it equal to 0, and you're going to solve for x. So a non-permissible value is x is equal to negative 2. So at x is equal to negative 2, this graph is not defined. So there's two different things that could happen here. It could be a vertical asymptote, or it could be a whole. So we have to choose, which one is it? Is it a vertical asymptote or is it a whole? So to find that out, we want to fully factor this rational function. So taking a look at the numerator here, notice that that's a difference of squares. So we can factor it. So it's going to be x plus 2 as a factor and another factor of x minus 2, a difference of squares. Okay, so notice when I factor that we actually have common factors to the top and the bottom. We have a common factor of x plus 2 on the top here and on the bottom. So if we have a common factor, that means this NPV at x is equal to negative 2 is not a vertical asymptote, but it's an actual whole in the graph. Okay, so to show you what happens at that point, I want to go and graph this on a calculator. So go into your calculator and graph the rational function. So you're going to plop in x squared minus 4, and also put brackets around the numerator so your calculator does not get confused on what you're doing here. Now you're going to divide by the numerator, which you're also going to put brackets around, so x plus 2. And we're going to use a Zoom 6 standard for now. So if you graph it, it looks like a simple linear graph. So it's a simple linear graph, but I want to take a look at what happens at this point, x is equal to negative 2. To see what happens at that point, go into your table. So go second graph to access that table. Notice at negative 2 that there is an error. So there's an error at negative 2 because negative 2 is a whole. So there's a point of discontinuity at that point. Okay, so that's my little introduction to a whole. Let's work on another example here. So my next slide says, for the following function, predict whether its graph has vertical asymptotes or wholes. And then you want to verify that using technology. So to identify if the non-permissible values are wholes or vertical asymptotes, what you want to do first is factor this rational function. So if we factor the rational function, what we get is, look at the top there. What do we have in common to both these terms here? Well, we could take out an x. So if we take out an x, I have x plus 3. Okay, so now we're going to factor the bottom. Take a look at each term. Is there anything common to each of those? Well, yes, we could take out an x. So if we factor out an x, we're left with x squared minus 2x minus 58. So as you can see, it's not fully factored yet. The numerator, yes, it is factored, but take a look at the bottom here. We have a quadratic right there. So try to factor that using your PSA method. So PSA, our sum is going to be negative 2. Our product is negative 15. And therefore, my two numbers are negative 5 and 3. So my two factors, or my factors on the bottom, are going to be like this. X and x minus 5 and x plus 3. So fully factor the rational function first. So we are fully factored. The second step is to actually identify what the NPVs are. So taking a look at my denominator here, we have 1, 2, 3 factors, hence we have 3 NPVs. And these NPVs are x is equal to 0, which comes from the first factor, and x is equal to 5, which comes from the second factor. And finally, the last factor gives me an NPV at -3. So those are my 3 NPVs. And now we're going to proceed on identifying whether or not these NPVs represent vertical asymptotes or holes. Okay, so look at the rational function after you factored it. So we're looking at this function right here. Are there any common factors? Well, if there are any common factors, what you want to do is circle them, identify them. So we have a common factor of x, and we also have a common factor of x plus 3. So if there's common factors, that means we have holes. We have 2 common factors, hence we have 2 holes. And those 2 holes are located at the corresponding NPVs of those factors. So since we have an x that's common, that means this is a hole. Okay, so that comes from the x values here. Since we have x plus 3 that's common to both top and bottom, that means x minus 3 is a hole. Okay, and x minus 5 doesn't have anything in common with the top, hence it's a vertical asymptote. So there we go, we have identified or predicted what happens at the graph where the NPVs lie. So we have 2 holes, one at x is equal to 0 and one at x is equal to -3, and a vertical asymptote at x is equal to 5. And to show this behavior, you can graph it in your calculator. So I want you to delete anything that you had in there before, and you're going to plug in the function. So go second quit, okay, and go back to y equals, and you're going to clear. And you're going to stick the original rational function into your calculator. So go back to the original function and plug it in. So put brackets around the numerator. We have x squared plus 3x over x cubed. So raise it to the power 3. Good. And minus 2x squared minus 15x. So if I graph this function, I'll use a Zoom 6 standard for now. I get a graph that looks something like this. Okay, so there's my rational function. We want to check what happens at the NPV. So we do have a vertical asymptote, and that vertical asymptote goes right through 5, which confirms this behavior right here. So at x is equal to 5, we have a non-permissible value. Now to confirm the holes, you go into your table of values. So go into your table, second graph, take a look at the table when x is equal to 0. Notice there is a big error there because it's not defined at that point, hence we have a hole. Same thing at -3. So go up to -3. Just give me a second here, -3. We also have an error at that point, so therefore it's not defined, hence it confirms our prediction that x is equal to -3 is a hole. So that is how you identify the vertical asymptotes and holes of a rational function.